It's a great honor for me to be here. It's really, I thank you for the invitation, for the opportunity to speak today. It's, as I said before, my first time in India, and it has been very, very nice. And I want to use this opportunity to tell you a story about atoms and light. And the story that I'm going to tell you explains how we can use atoms and light to construct atomic clocks. Atomic clocks, as I will explain, are not only incredible timekeepers, but also we are using these systems to actually explore the quantum realm. So hopefully, through this talk that we are going through the inner workings of atomic clocks, I convince you how exciting these systems are. And well, you get at the end of this lecture as excited and thrilled to start learning more about these systems. So, okay, so let me say that I'm not the clockmaker. I am a theorist, but I have the fortune to collaborate very closely with Professor Junji. He's at JILA, and he's actually the experimentalist. This is some of the pictures of his group of grad students and postdocs over years. And when I do the theory, this is my theoretical group, and these are some of the students that have contributed a lot to this story that I'm going to tell you about today. All right, so let's start very broadly. So maybe just to understand what I mean by ultracold atoms, that is what we are going to use to create the clock. So of course, ultracold means that there is a temperature related to the system, and remember that the gas, the temperature is a measurement of the kinetic energy, or the average kinetic energy of atoms in the gas. So when we look at the temperature and we use a thermometer, Kelvin scale, for example, we know that atoms at room temperature, the molecules are moving extremely fast at the speed of sound, 300 meters per second, and therefore it's very hard for us to control the system. And if you try to think about what is the coldest temperatures that you can imagine in our universe, you might think, oh, well, the temperature of the outer universe, that is of the order of a few kelvins. And if I do the conversion, for example, 4 Kelvin is the temperature at which helium condenses. And still, however, this temperature, the atoms are moving at 90 meters per second, so too fast. So one of the biggest developments that we have had in these recent years have been the possibility to cool down atoms to very dilute gases of atoms, 10 to the 4, 10 to the 6 atoms, to temperatures of 10 to 100 nanokelvins, very cold, at which at these temperatures, the atoms are moving at velocities of centimeters per second, and the density is very dilute, I mean 5 orders more dilute than air. And we are using these systems then to control them and explore many aspects of physics. And actually this reflects, I mean, the work of many scientists in the field. So for example, to be able to cool down the atoms using lasers, that's called laser cooling, but was recognized by the Nobel Prize in 1997, Tanuji, Steve Chu, and Bill Phillips at Maryland. And then, nevertheless, this temperature was not enough. So they used lasers to actually reduce the kinetic energy of the atoms by absorbing or emitting photons. However, the temperature of microkelvin is not enough to create the conditions that we want. And it was later in 2001 where scientists at JILA, Eric Cornell, Carl Wyman, and at MIT, Wolfram Ketterlich, were capable to reduce the temperature even more by thinking of the atoms as, imagine that it was a coffee, and then the hot molecules of the coffee can escape during the evaporation, and then you can get the coffee much colder. So they did evaporative cooling of the atoms and were able to reach temperatures at which pure quantum phenomena manifest. So the atoms form what is called a Bose-Einstein condensate. And this was a very important development. The question is, when we have such cold gas of atoms, what we can do with it? I mean, what opportunities these ultra cold gases offer to us? And what I'm going to tell you today is how we are using these systems as a window to explore the quantum realm. If you think what could be or what are the holy grails that we are now in our community or in physics in general. So we wanted to use fully controllable systems for creating advanced materials that cannot appear in nature as per se. So, but we wanted to engineer conditions where these systems, for example, superconduct at room temperature. I mean, but these are in general very complicated questions. Of course, we want to use these systems to build new type of technology that is really advanced and can break many constraints that we have with current computers. So quantum computers operate with quantum mechanical elements themselves and can therefore understand quantum mechanics and shed light in very different questions that we don't understand now. Of course, there are many questions about our universe that we don't understand. One key question is the unification between the quantum mechanical world to the macroscopic objects ruled by general relativity. So this connection between quantum mechanics and gravity remains a very important open question. And well, perhaps we want to use our systems to create sensors that can measure in a way that surpasses all what we can do with just classical objects. So I think these have been the holy grail of our community for many years. And the story that I want to tell you today, and hopefully I convince you, is that ultracold atomic systems are allowing us to explore all these different directions, but in particular atomic clocks. And I'm going to explain a little bit how these systems are in fact contributing step by step to all these different directions. Okay, so let's start very basic. Let's start discussing at clocks in general. So we know that a clock is something that ticks in a regular, repeated manner, and we use it to measure time. So what is important is that all clocks have two very basic ingredients: the oscillator, that is what ticks, and a counter, that is an object that allows to count the number of oscillations and with that keep track of time. So in the case of atomic clocks, there is no difference. So we are going to have an oscillator. In this case, the oscillator is an electromagnetic wave. And the counter, in this case, are the atoms. The important difference is that we are using electromagnetic waves that are so fast that even standard electronics cannot count it. The ticking is extremely fast, and only atoms can do that job. That's one of the advantages of atomic clocks, as I'm going to explain. All right, so why we are using atoms to build clocks? Well, it's because we are exploring at the heart the properties of quantum mechanics. That is the idea that the energy in the atom is quantized. And not only quantized, but universal. So the energy splitting of an atom here in India is the same that an atom in the US, everywhere. So it's not subject to mankind errors when we construct it. So this is what it provides an unrivaled definition of the second, this energy splitting. And in fact, this was used to create atomic clocks since 1955, where the first atomic clock was done by Essen and Parry. And then in 1967, we used, in fact, the energy splitting between the two lowest hyperfine level of cesium atoms to define the second. Basically, we define the second as certain numbers of periods of radiation that is resonant with this transition, and we count them this specific number to form a second. For the case of cesium, it corresponds to this number, about 9 million periods of radiation, and this is how we actually define the second. The interesting part is that the cesium clock, that is the standards, is not the best in the world now. And let me explain why. If I show you these two rulers and I ask you which ruler is more precise, A or B? I know that you are all telling me ruler B because it has more ticks, more resolution, so I can measure better. Exactly the same for clocks. What happens is that the cesium clock, the ticking that is determined by the energy splitting of the levels, is much slower than what we can actually have. It happens that the clocks operate with microwave transitions that have energy splitting of gigahertz that are relatively slow. On the other hand, we can use clocks that use optical transitions. These optical transitions can be 4 or 5 orders of magnitude larger than the cesium microwave transition. Therefore, the ticking is much faster, and therefore we can have better resolution to determine time. All right, so we wanted therefore to build clocks that uses optical transitions, but the point is that, of course, not all the atoms are good for that. So an optical atomic clock has the laser and the atoms, but the atoms have to be very specific type of atoms. And then, of course, the next stage is to lock the frequency of the laser to the frequency of the atoms. And for that, we are going to do some type of spectroscopy that is important to determine. I mean, we wanted to make the frequency of the laser equal to the frequency of the atoms. But let's go step by step. And as I mentioned, not all the atoms are good for optical clocks. Why? Well, all atoms have optical transitions, but the problem is that we need optical transitions that are very long-lived. So, and in this case, this property is satisfied by alkaline air atoms that are atoms that in the second column of the periodic table, all others with similar structure like ytterbium, for example, here, and they are characterized by having 2 outer electrons. So the important part is that, well, for the clocks, we not only are going to care about the electronic properties, but also we are going to care about the nuclear spin. It happens that fermionic isotopes have nuclear spin larger than 0. And in the case of strontium, for example, that is our favorite atom at JILA, the ground state and the excited state can have, in addition, 10 different nuclear spin states that we're going to use in principle for our advantage. Okay, so the important part, as I mentioned, is that the optical transition that we are going to use in the case of strontium is super long-lived. So we have an optical transition between a ground and excited state that is dipole forbidden because we are going to go from j equal to 0 to j equal to 0, some selection rules that happen in quantum mechanics, and from singlet to triplet. So it's not totally forbidden because of the nuclear spins. Actually, this is what allows this transition to happen, and the lifetime of this transition can be as long as 118 seconds. So this is super long, and that allows us to take advantage of these unique properties. In fact, if you imagine or try to make the analogy of this transition as a classical pendulum, and you assign a quality factor that is the rate between the ticking and the damping coefficient, this quality factor associated with this transition is larger than 10 to the 17. So it corresponds to a pendulum that when you will start to let it swing, would swing for the entire edge of the universe without damping. So a very, very, very good pendulum. Of course.
So what sets the quality factor?
The quality factor sets that, I mean, in this case, that this transition is very long-lived because it's forbidden. So that's what says.
The width of the...
The quality factor, yes, is the lifetime. I mean, the frequency is an optical 10 to the 14, and the line width is just, or associated with the damping rate that is just millihertz. So because the lifetime is 100 seconds. So this is what said this very atom to be super long-lived, super good for clocks.
That's why you needed to have a long length.
Exactly. Just we wanted to look for a very long time in order to spectroscopically resolve the levels, because that's what we can. So besides that, of course, we know that, as I mentioned, the clock is not only the atom, but the laser. So we have to develop very, very good lasers that are taking advantage of this very narrow transition. And this is when you at JILA has been able to develop very, very, very coherent lasers with quality factors that is larger than 10 to the 16. So, so lasers that remain coherent for 10 or 100 seconds at that time. Finally, as I mentioned before, we have the laser, we have the atoms, but we need to be able to lock the laser frequency to the atomic frequency. And for that, we need first to make sure that my atoms are not going to blow away when I illuminate them with the laser. This is a very high energy transition, so we need to trap the atoms. But the problem is when we trap the atoms, then we can perturb the energy levels, and this is not good. So they have shown that we can trap these atoms with lasers, forming what is called an optical lattice. We interfere lasers, and then the atoms are trapped because they induce dipole moment in a periodic potential. But the important part is that the periodic potential filled by the ground and the excited state is identical. This is called magic lattice, magic wavelength. This has been developed for strontium atoms. And when we trap them, the advantage is that the atoms are not subject to Doppler shift that could change the transition, because if we trap them, we prevent the motion perpendicular, parallel to the laser direction. The only motion is perpendicular, and therefore we are not affecting the frequency that we measure because the atoms are moving. So we trap them and we remove the Doppler shifts or recall shifts. The atoms are not flying away, and we remove any frequencies from the light that we used to trap, that is no star shifts. So this makes these systems ideal for clocks. So now, in order to lock the atoms to the laser, so what we use is a protocol that is called Ramsey spectroscopy in honor to Norm Ramsey. He received the Nobel Prize in 1989 for that type of sequence. Basically, for that, we imagine the atom as a two-level system, but we visualize it in what is called a block sphere, where it's a sphere where if the atom's in the ground state, the arrow is pointing down. If the atom's in an excited state, the arrow points up. And if we have a superposition, then the arrow is, for example, if we have equal superposition between the ground and excited state, the arrow is at the equatorial point. So the idea is that we have the atoms in the ground state. We're going to illuminate them with the laser with some frequency that we want to match with the atomic transition frequency. So for doing that, we first create these strong pulse of light. And what we do is that we drive a superposition between the ground and excited state. This is what we, and the superposition is set, the magnitude of the excitation is set by how long I illuminate my atom with the laser, and determined by this tipping angle theta, that is the Rabi frequency by the time I eliminate it. The Rabi frequency is the strength of the laser. So basically, as I said, then I create a superposition between the ground and excited state. And then what happens is that I let the atoms precess in the dark. So I turn off the drive and I go into the rotating frame of the drive. And what happens is that the frequency of the laser and the atom are not locked. Then it's going to, the important parameter is the detuning, that is the frequency difference between these two. And therefore, in this rotating frame, the excited state is going to acquire a phase that is different from the ground state. And this phase is what we wanted to measure because it tells us how different is the two frequencies. So visualize this phase can translate as a rotation in the XY plane of the block vector, and we can infer this frequency by applying a second pulse that transfer the phase accumulated into population. We measure the population, and by measuring the population, we get what is called a Ramsey fringe, and the frequency of the Ramsey fringe is of this oscillation is going to tell me when my laser is locked to the atomic frequency. Not only that, but we wanted to make this measurement for a very long time. So not only the phase but the contrast, because the longer that we look at these oscillations, the better we can log our laser to the frequency of the atoms. So now you can see that in all this, I put an N. The important point is that the more atoms that I interrogate, the best, because I have a larger signal. Imagine that all atoms are behaving exactly the same. So we have many times copies of the system, and therefore we can measure statistics better. And that's what June was very excited about. Before, most of the clocks operate that were optical operate with a single ion, but June wanted to push the idea of operating clocks with neutral atoms, because we can interrogate many atoms, and when we interrogate many atoms, we can have better signal to noise. Actually, for for uncorrelated atoms, this signal to noise grows as with n as the square root of n. So the more atoms, the better. But the problem, however, is that atoms are not transparent. So these atoms, when we put them in the clock, start to collide. And the issue is that when they collide, the frequency of the transition that we measure is going to be affected by the density, by how many atoms we have. And this is super bad. But June is a very smart person and said, okay, the way that I'm going to deal with this problem is take advantage of the quantum properties of my particles, and we are going to use fermionic atoms. These fermionic atoms are very cool, as I'm going to explain why, and moreover, Debbie Jean, unfortunately she's not longer with us, taught us how we can cool down fermionic atoms to very cold temperatures. Okay, so why fermionic atoms are better? Because when atoms collide, again in quantum mechanics, everything is quantized. So we have to understand the collisions in terms of a quantized angular momentum of the colliding particles. Now, the point is that atoms collide, and therefore they get very close to each other, and then they scatter away. And at the end, because of energy and momentum conservation, the effect of the collisions when they are far away is only a phase shift. So this phase shift, when the collision happens at very cold temperatures, depends on the angular momentum and the momentum of the collided particles, and have a universal behaviors that is characterized by certain parameters that depend again on the angular momentum of the colliding particles. The lower energy collisions corresponds to L equal to 0. That's what we refer to as wave collisions. Then they are characterized by a parameter here in this threshold laws that is called scattering length. It measures the strength of the collisions. But importantly, these collisions that are associated with is also a centrifugal barrier. For L equal to 0 atoms, this barrier disappears. So that's why these L equal to 0 correlations are the most prominent one. On the other hand, if we go one level up, the L equal to 1 collisions, the P wave collisions, they have a centrifugal barrier. The centrifugal barrier is going to prevent the collisions to happen. It costs energy for the particles in one hand. And well, in our case that we have atoms in the ground and excited state, you can see here L equal to 1, it costs energy, that is why it's proportional to K squared, K associated with the momentum of the colliding particles. And then there is a scattering volume that can have in 3 flavors between the ground and excited and ground and excited. So they are suppressed by the centrifugal barrier on one hand, but moreover, if we use fermionic particles, it happens that this L equal to 0 channel is forbidden for identical fermions, because identical fermions cannot collide by the L is equal to 0. And that's why June said, okay, I'm going to use identical fermions, that the only way that can collide is via the L equal to 1 channel. This is suppressed by 30 microkelvin, that is the barrier. And if we have a gas that is below 1 microkelvin temperatures, then we are not going to worry about these P wave collisions. So that's what he tried to do. And Fortunately or unfortunately, the clock was so precise that even these very weak peak wave collisions used to be the second largest systematic in the clock back in 2009. So no, there is no choice. We need to understand the interactions of the atoms in the clock. And that's where the theory comes into play. So remember that we were using an optical lattice. So this periodic potential generated by light to try the atoms. The clock typically operates with one D optical lattice where the atoms are able to move freely in the direction perpendicular to the lattice. So it's a bunch of pancakes, and in each pancakes, atoms can move almost freely. We have not a quantum degenerate gas, it's a microkelvin gas. So you can imagine this pancake as an harmonic oscillator where the atoms are going to occupy the quantized energy levels in a thermal distribution. So the atoms are going to populate these different thermal levels. The energy splitting, however, between the harmonic oscillator levels is of the order of 500 hertz. So much more higher, much larger than the weak big wave interactions. So this is where we are going to notice that collisions, because the P wave, the weak P wave interactions cannot change the energy levels of the atoms in the harmonic oscillator because costs too much energy. And the only thing that can happen is that the atoms flip the spin without changing the motion. And if we have a system where the atoms only have a spin degrees of freedom without any motional degrees of freedom, then we can model as a spin model. So basically, we can imagine these energy levels, motional levels, and as an energy lattice where the atoms are pinned. So in this description, where we have atoms pinned in this energy lattice, nevertheless, because the wave functions in these harmonic oscillators are highly delocalized, what happens is that the interactions can be seen more or less like all to all. So the atoms, even though the interactions are very localized in position, in momentum or in energy space are quite delocalized. So that allows us to think of the spin of the particles not as the individual spin of each atom, that would be very complicated, but instead we model the system as a collective, in terms of collective spin, just the sum of every spin of the atoms. So for example, SC is just the number of atoms in the excited state minus the number of atoms in the ground state. And the interesting part is that during the clock interrogation, this SC is only depending of the initial pulse. Remember that at the beginning we do a pulse that transfer atoms from the ground to the excited state. This angle theta is set by the initial pulse and remains fixed. So the important part is that therefore the collisions of the atoms in very simple terms can be modeled by a very simple Hamiltonian that can tell us how different the collision is modified by the presence of the other atoms in the array. Basically, these parameters instead, not only have the detuning that I defined before, but there are other parameters that determine the collisions of the clock, and these chi and Cm parameters, or C parameters, depends on the scattering volumes of the big wave interactions. The important part, just to summarize the story, is that at the mean field level, the effect of these nonlinear terms is like having an effective magnetic field that changes the detuning, and in a way that depends on the inversion that is set by the initial pulse area. Basically, we have that a very simple model where the ticking of the clock is going to be modified by the collisions depending on the excitation fraction that we do at the beginning of the pulse. That was the prediction, and in fact, that's what the experiment saw. The difference in the ticking rate of the clock is going to depend on the excitation fraction in a very simple way. So with that very simple theory, we were able to operate the clock at a point, at an excitation fraction, where there is no change in the collision rate. And this is what allows us to actually improve the clock and get rid initially of the role of the collisions. Actually, there is still some inelastic interactions that didn't change the rate of the clock, the ticking rate, but it reduces the time. But anyway, by controlling the collisions and letting them not be a problem, we were able, in collaboration with June, to create a clock that was 1,000 times better than the current scission standard back in 2014. So this corresponds to a clock with a fractional uncertainty of 2 times 10 to the minus 18. That means a clock that never gain or lose 1 second in some 15 billion years. That is roughly the age of the universe. That sounds very good. But the most exciting part is that in the last few years, we have been able to improve the clock even 1,000 times better by further understanding the many-body physics of the atoms in the clock. And this is the story that I want to tell you briefly about. So,
when you have many of these atoms, the nuclei of the different atoms, their interactions are not important?
They're not important. I mean, we are going to be spin polarized. The nuclear spin, I mean, in this case, they just polarize the atoms in a single nuclear spin. Okay. And well, maybe sometimes they use the contrast between the minus 9.5 and 9.5 to remove some magnetic field effects. But at the moment, they not participate in the collision, in the dynamics. So, but this can lead to this idea. Actually, the interesting part is that if you think at a single strontium atom, what I mentioned is that there is an orbital degrees of freedom, the clock state, the ground and excited state are very long-lived. We have a nuclear spin state that can have even up to 20 levels in the ground and in excited state. And this, if you think about the strongly correlated materials, is the interplay between orbital spin and charge degrees of freedom that makes this system so very exciting. So we have orbital degrees of freedom, spin degrees of freedom in the strontium atom, and the only part that perhaps we don't have directly is the charge, the fact that the atoms are neutral. But what I'm going to tell you now about is that strontium atoms in an optical lattice behave like charged electrons in a magnetic field. And this is going to be very important to understand the collisions. Well, a disclaimer of a note. So in fact, the spin-orbit coupling has been a very important effect that not only determines the atomic properties or the electronic structure of atoms, but for example, in solid state materials, is very important for spintronic devices and even at the heart of topological insulators. And for example, there are beliefs that if you have a topological insulator close to a superconductor, you can generate some type of Majorana particles that could be useful for topological quantum computer. And in fact, this is an effort that Microsoft has been trying to push very strongly. So the point is that spin-orbit coupling happens naturally in our clock, and we don't have to do anything else except to reduce the depth of the lattice potential that traps the atoms. So basically, we have a laser that is interrogated by atoms. This is the 1D lattice. If the lattice is very deep, well, the atoms cannot move from one lattice side to the other. But if the lattice is shallower, they start to move from one lattice side to the other. The important part is that the wavelength of the laser that we use to interrogate the clock transition is optical, as I mentioned, and therefore comparable with the lattice spacing that we use to trap the atoms in this magic potential. So that means that k time A is not a negligible quantity, so k times A can be of the order of pi. What does that mean? That the phase of the laser clock changes significantly from one lattice side to the other. This means that when I interrogate my atoms, they're going to rotate in and behave different if I go from one lattice side to the next. And even if the atoms are not able to tunnel or to explore the neighbor, that's okay. But as soon as we reduce the lattice depth, one atom in here is going to see that the neighbor has a phase that is different to what they have. And this is at the heart of this spin-orbit coupling. Let me explain a little bit why. And this experience when we allow the atoms to tune. So one way to see that is that, well, if I let my atoms move along the lattice that traps in the clock, then the dispersion relation is going to have a sinusoidal dispersion that is because of the periodic structure of the lattice. And identically for the ground and excited state, this is the energy versus quasi-momentum or momentum in the lattice, that is only different via the tuning between the ground and excited state, because that's how we constructed the magic lattice. It has to be identical for the ground and the excited state. But now we know that momentum is conserved. So if I take an atom from the ground and move it to the excited state by absorbing a laser photon, the photon that they absorb from the laser has significant momentum and therefore connects an atom with quasi-momentum Q naught in the ground state to a quasi-momentum Q naught plus the momentum of the laser that is absorbed from the photon. So this means that I have a spin flip that is accompanied by a change in the motion. So another way to visualize is that this is connecting the ground and excited into different quasi-momentum. I can also do what is called a gauge transformation, where I relabel the levels of the excited state. And in this case, you can see the energy. I still am connecting an atom in momentum Q. Now it's diagonal with an atom of momentum Q plus the laser momentum. But in this case, the way that I can visualize it is more in a diagonal way. So basically what I can see is that I'm changing an atom from the ground to the excited state, but now the excited state, because have different momentum, have the momentum of the photon, is going to have different energy. So that means that if I try to see my atom as a two-level system, and when I illuminate my atom with the laser, I not only change the transition from ground to excited by a radio frequency, but also the energy of the ground and excited state are going to depend on the momentum. This dependence of the momentum of the magnetic field with the momentum of the atom is what characterizes spin orbit coupling. So basically what happens is that now the eigenstate of my system is going to depend on the momentum of the atom. So the orientation of my spin is going to depend on in which quasi-momentum I have. So basically the energy split in between these two levels changes as a function of the quasi-momentum. Another way to visualize the same idea is with what is called synthetic ladder. In synthetic ladder, what we do is that we have the ground and excited state as the two legs of the ladder, and they are coupled by the laser, because an atom in the ground can become an atom in the excited by absorbing a photon. But the important part is that because the laser has different phases depending on the position of my ladder, what happens if I start with an atom in the ground state, I absorb a photon to go to the excited state at lattice side 1. Then my atom can tunnel from the excited state in lattice side 1 to lattice 0. Then I emit a photon from lattice side 0, but the phase of the photon is different because they have different phase, different location, and therefore after I do a closed loop, I acquire a next phase that is set by the phase of the laser. This emulates the Bohr-Aharonov effect of phase that acquires an electron in the presence of a magnetic field, and therefore generate an effective flux. So this is what it tells me, that atoms can behave kind of as a charged particle. So we checked this effect of the spin orbit coupling when we were having a very dilute system in the clock. In fact, we were able to prove that. Basically, what we did is that by changing the laser detuning, we changed the position of the bands that were populating the atoms. So basically, for example, at this detuning, all the atoms were in the ground state. We illuminate them with a very weak laser that transfer only atoms that are very resonant in energy. We blow up all the other atoms, and therefore, by doing that, we selected a narrow window of momentum of the atoms. And we can change the detuning to different type of crossings, and therefore, by doing that, we change the momentum of the atoms of the excited state that we prepare. And when we did that, then we let the system evolve. And because, as I mentioned, the eigenstate of the system depend on the momentum. Depending on the momentum window that I chose, the atoms are going to have different precession rates. And in fact, that's what happened by depending on the momentum window that I chose, the rate of transfer between the ground and excited states in the presence of the drive was going to depend on the initial momentum window, confirming that we have a spin orbit coupling in the clock. So that was good that we were able to actually understand that there is a spin orbit coupling in my clock, but at the same time detrimental. Why? Because, well, if this was to check that there is a spin orbit coupling when the system was super dilute, but as we start to put more atoms, I told you that the S-wave interactions were suppressed for identical fermions. But if we have fermions that are distinct because they are going to have different phase depending when they are, when I let my atoms tunnel from one lattice side to the other, then I open a route for S-wave collisions and therefore very badly affect my clock. Now the clock, if I reduce the lattice depth, my atoms in the clock are going to really be screwed by these strong collisions. Okay, but in order to rescue, we tilted my clock in the other direction. So in this horizontal direction, the atoms were going to have very bad effects when we reduce the lattice depth because of the spin orbit coupling. But the next step was trying to make the clock vertically and use gravity to our rescue. So what we built, the next generation of the clock, what we call a Wannier-Stark 1D lattice clock. That is a clock that operates vertically. The advantage is that I operate vertically, then my eigenstates of the atoms in the clock, instead of being fully delocalized, now are becoming more localized because there is an energy penalty from moving from lattice side to the other because it costs energy to climb the stairs. So basically, the energy from one atom in one lattice side to the next is MGA, that is different, and this helped me to localize my wave function because it costs too much energy even in relatively shallow lattice. So what happens is that as I make the lattice shallower and shallower, the Wannier states that are the eigenstates of the systems that are a superposition of localized Wannier orbitals. This is just by some weight. I mean, the important part is here, the cartoon. You can see that even at very shallow lattice, instead of the wave function to be totally delocalized, because of the penalty of the gravity, the wave function remains highly localized. So why is this useful? It's a win-win for many aspects. So I saw this picture that from badminton here. So that's what I say, it's a win-win-win. So what are the advantages? So I have my atoms in the clock. If I make my lattice shallower, then at my lattice shallower, in principle, is super bad because then atoms are going to move, they are going to be a spin orbit coupling, and they're going to collide and be very bad. But if I make the clock vertically, my atoms are going to more confined, and therefore I can delocalize my lattice without having too much decoherence, making the coherence time much larger. Furthermore, if I decrease the lattice depth, then the point is that the atom in each lattice side are going to feel a less interaction because if the lattice is shallower, the density decreases and therefore collisions are also less affected. And furthermore, there is what is called light scattering because the atoms, when they are trapped in the optical lattice, they are going to still scatter light from the lattice, and the lifetime is going to be worse the deeper the lattice is. So if the lattice is shallower, therefore they are going to not only suppress these bad inelastic light scattering collisions, but also I want to suppress these detrimental collisions that I was showing that were affecting the clock. So,
when you put it in this vertical setup or tilted, don't you have to worry about the gravitational redshift?
Okay. Yes, this is going to be, yes, and this is going to be the next part of the story. But when we are going to worry about the gravitational redshift, but when we're very, very sensitive, when it's going to be very small. So indeed, well, first is trying to understand if it's in vertical lattice, we can use the interplay of spin-orbit coupling, collisions, and gravity to suppress interactions all the way. And we were able to do that by operating what we call magic depth. Now, not magic wavelength, but magic depth. And this is what we try to explore. So now our clock is vertical. So instead of this, there is an harmonic oscillator states in each of the pancakes, but along each of the lattice sides, there is going to be Wannier states. So atoms are going to be now localized in these harmonic oscillators plus Wannier states. And if I try to see the collisions between the atoms in the different parts of the lattice, we are going to have the same on-site collisions that I described before that are purely P-wave because the atoms are identical in each lattice site. But now between atoms in different lattice sites, there is going to be a little bit of S-wave collisions because atoms have different phases in different lattice because of the spin-orbit coupling. So the important part, however, is that, well, between nearest neighbor lattice sites, we have very bad, very strong S-wave interactions. I put them as the UAG, very strong interactions, but the overlap between the wave function is small because of the gravity. So this compensates and it can make the S-wave and the P-wave interactions of the same level. And therefore, when I look at what is the effect of the collisions for a specific lattice depth, I am able to make all these collisions cancel, suppressing again the bad effect on the clock. And that's what the experimental saw. So if we look at the ticking of the clock versus lattice depth, we predicted that at a specific lattice depth, the S-wave and the P-wave collisions can cancel. There is not bad ticking at this of the clock, and we can recover all what we wanted in the clock. No collisions, long coherence time, no effects from detrimental losses. And in fact, by operating at this point, the clock was able to report a sensitivity to collisions less than 10 to the minus 21. And because of the longer lifetime in this shallower lattice, in this vertical position, they were able to reach 37 seconds of coherence time. That was super exciting because, not only tell us the interplay between many body physics and optical lattice clocks, because we were able to, on one hand, use many body physics to build a better clock, and then use the better clock to understand better physics. But now we were starting to start in a regime where we are going to be sensitive even to more effects. In fact, Einstein told us that clocks at different heights are going to tick at different rates. And actually the differential ticking of the clocks at different heights is depending by very simple parameters. G, the gravity, H, the different height, the height between the two clocks, and C, the speed of light. And what happens is that this value can be of the level of 10 to the minus 19 when H is of the order of a millimeter. And actually we were reaching the sensitivity of that at that level. Prior experiments operating with ion clocks were able to measure the redshift of the order of 30 centimeters. But now, by the longer coherence time, we were able, in fact, to keep track of the ticking between the two parts of the clocks and actually observe that they were ticking at a different rate that actually matches exactly the 10 to the minus 19 in a millimeter distance. In fact, this is data that we're taking over a few days that confirm, in fact, that there is this minus 10 to the minus 9 systematic in the clock because of GRG. So this is very exciting because it's opening really new opportunities to actually explore GR in very exciting directions. Now, even at the quantum regime, where maybe even entanglement is going to start opening a new window. So I'm running out of time, so let me say that the next generation of atomic clocks is going to move towards more quantum behaviors. So the new generation of clock actually operates in a 3D lattice, not only 1D lattice, but 3D lattice, and operates with a quantum degenerated Fermi gas with very cold temperatures. In 2019, actually, in this 3D lattice, the experimenter reported records of coherence of atoms in an optical lattice, coherence time of the order of 12 seconds. And now, in the latest experimental implementations, we have been able to cool down the gas in the lattice, in the 3D lattice, reaching filling fractions very close to 1. And when we have filling fractions very close to 1, we start to simulate the behavior of fermions moving in a ultracold fermions, moving in a 3D lattice potential. And this system is described by the so-called Fermi-Hobart model. The Fermi-Hobart model in condensed matter describes the motion of electrons in a 3D crystals or in a 3D, 2D crystals characterized by a nearest neighbor hopping by on-site interactions, because when you have two particles with different spin, they're going to have interaction energy U. But in addition, we are going to have a spin orbit coupling when we drive the clock from the ground to the excited state. The advantage is now that, in contrast to the 1D lattice, where the spin orbit coupling was detrimental, in the 3D lattice, we are able to orient the orientation of the clock laser at very different directions. If we have 1D lattice, we can only point the clock laser along the strong lattice direction, because in the weak direction, they're going to blow apart. But if all the dimensions are trapped, then we can orient the lattice the clock laser as I want to. And for example, I can make the motion only happen in one plane and not in the other. In that case, for example, if I orient my clock laser vertically and the motion is along the XY plane, there is no spin orbit coupling, or I can make the spin orbit coupling as large as I want. This phase can be equal to pi, making the spin orbit coupling the strongest possible. So the last part that I wanted to measure is that now if the particles are moving in the lattice, then there are other type of interactions that start to play a role that is called super exchange interactions. These are the ones that determine also the behavior, for example, of cuprate superconductors, for example, when they are unit field. That means that if I have very strong interactions, an atom can tunnel to the next side, see the neighbors, and have to tunnel back because the neighbor costs a lot of energy. So these generate spin-spin interactions between atoms that are these atoms are barely moving, but when they move, they see the neighbor and see that the spin is different to what they have, and therefore it costs energy. So the advantage is that now when we are going to have our super exchange interactions can be even more complicated because we have the spin orbit coupling in place. That means because there is the clock laser that have different phases in one lattice size to the other. So the interplay between spin orbit coupling and super exchange give rise to much complicated models of magnetism. For the conductors in the audience, it can give rise to models like XXZ models of what is called anisotropic spin-spin interactions. And these are going to affect the ticking of our clock. So our next effect is trying to understand how these more complicated Hamiltonians are going to modify the ticking of the clock. The important part is that if I have interactions that are in the form of sigma dot sigma, they're SU2 symmetric, so they're not going to affect too much the ticking of the clock. But when we have the spin orbit coupling interplay, they are going to do it. So in the last few years, we have been able to actually keep track of this super exchange interaction in the clock, because we were able to try to now interrogate and try to see how the atoms in the clock tick across different regions, compare the different ticking and how they depend on the tunneling and lattice depths. So basically, well, now in addition, we have been able to implement new type of dynamical decoupled techniques that allow us to remove some undesired single particle noise. And with that, we have been able to change the lattice depth along the vertical direction, along the horizontal direction, control the geometry of the lattice, and understand how the clock is ticking under different lattice geometries. And in fact, what we saw is that depending on the lattice depth, we see that now not only the ticking of the clock, but the contrast of the fringe that happens during the experiment is going to be, okay, I'm almost done, is going to be reduced by the presence of these collisions. But the important part is that we have been able to show that these collisions all collapse into the same form that is consistent with super exchange interactions. So we have for the first, and moreover, we changed the density of the atoms, but this is still localized particles, so we were able to check that everything is consistent with super exchange. So with that, I want to say that now we have the tools to also control interactions in a three-dimensional lattice, and with that, we can enter the fully quantum regime where we are going to use interaction itself to entangle the atoms and enter the new regime of non-classical clocks. We wanted to be able to use these interactions to generate new type of entangled states that could be useful for quantum computing. We have been able to we were going to be able to use this interaction to generate, for example, flat states as a proof of principle for error correction. And finally, we can use not only the two nuclear spin the two levels that I have used by choosing one nuclear spin state, but take advantage of the 20 different nuclear spin states to explore new type of quantum magnetic phenomena that is called SUN magnetism. So hopefully with that, you can see that is great vista ahead. We will try to create even better clocks with entanglement. We wanted to try to use them for setting proof of principle, of course, not quantum computers, but for proof of principle for quantum computers, and hopefully push the exploration of gravity in the regime with quantum mechanics start to play a role. And with that, explore even the ripples of our space-time. And with that, thank you for your attention.
Let me thank Saray for such an enlightening lecture. I'll hand it over for the question.
Then we have time for a few questions.
The fermionic optical lattice clock has surpassed the cesium fountain clock in accuracy, for the last few years. So when do you think the international time standard will be changed to the new, much more accurate time standard?
Yes, I mean, we hope that soon. It requires a minimum number of clocks that are operating with alkaline atoms. And well, we have efforts around the world in Europe, in China, I mean, there are in Japan. So hopefully there is going to be many systems that they can compare to each other and then allow us to change the standard in that way. So I don't know the specific time, but we're optimistic that in the next few years.
Yeah, actually, as a follow-up to that, and the question I was asked is, so if you're so sensitive to the redshift, the gravitational redshift, how can you compare?
Yes, we will have to report the height, and actually there is a geodesic system. Now June has to go to experts that are going to track geodesics, and you have to report your measurement of the clock with your position in Earth in order to coordinate. Yes.
So how do you do that, the geodesic?
Oh, they came to JILA. I don't know. They came to JILA and they can follow the I don't know.
So they're mapping the
gravitational potential and then across exactly. And I think, yes, I mean, it's unavoidable that we have to report the height when we report the frequency of the clock.
And somewhat, again, another question. This line, I've heard recently they have these thorium, they have these nuclear clocks. Do you have any comments?
Yes, I mean, this is a very exciting prospect in the sense that all these clocks, they're great, but they require very complicated vacuum. They are not easy deployable. So the hope is that if we can have a thorium clock in a solid state setting, it can be miniaturized and operate in a simpler way. Still, the systematics of a solid state system are complicated. So it's not clear that is going to operate as a clock that surpasses, for example, the strontium clock in the short term, but maybe for sensitivity of fundamental constant variation, something that is differential and not absolute, then maybe this is where it has more promise.
Hi. So in what you described, basically there was a fundamental assumption that the constants of nature, like the electric charge, Planck's constant or the gravitational constant, are basically time independent.
Mm-hmm.
Now, do you have some comments on that? Because it's a very
Yes.
important question.
No, that's an excellent point, and I think, for example, it's believed that maybe dark matter can change and can the time. I mean, the fundamental constant is time, and in fact, there are experiments that are bounds that you can have by measure. For example, in the crystalline cavity, he can try to understand. Place bounds on this change of these fundamental constants. This is something that should be explored in the future, and is one direction where clocks become useful, specifically, for example, the thorium clock that seems to be more sensitive. So this type of sensitive to fine structure constant changes are one of the predictions for these thorium clocks.
Is there any advantage in bringing reverse state?
The question if it's advantage of bringing reverse states. Well, Adam Kaufman at JILA is trying to build a clock using optical tweezers. So the question is, in these clocks that we have, we operate with 10 to the 3, 10 to the 4 atoms. That, well, is good. But maybe at some point what you want to operate is a clock with only 100 atoms, but similar sensitivity. And this is where maybe next generation of clocks operated in optical tweezers and entangled via Rickware interactions, for example, could be an opportunity. So, it reduces the number of atoms, so it will require entanglement in order to be something that, a system that operates at the level that these larger number of atom clocks. But it's very exciting. I think it's something that is progressing.
Any other question? From students? Okay. If not, let's thank Anna for very beautiful talk.